Okay, let's look at passage 6. So first question, everybody, is this going to be a do now or a do later? Who thinks this is a do now? Okay, so why would this one be a do now? Okay, what about do later? Who thinks it's a do later? Okay, so why do you think it's a do later? Okay, so notice that you can have different strokes for different folks. Some of you might prefer doing it now, some doing it later, depending on your strengths, your weaknesses, your preferences in terms of topic, etc., etc. But make sure you make that decision up front because you want to save, as we've talked about, the hardest passages for the end. Okay, let's map it out. We talk about thermodynamic cycles. Okay, so it mentions a transfer of energy, and we see heat, we see work. You can highlight those as topics that you're going to have to deal with and concepts. We also have highlighted a heat engine and a heat pump. Okay, and we're told that clockwise loop represents a heat engine and a counterclockwise loop a heat pump. So italicized things are things that you want to take note of. Moving on to the next paragraph. Heat engine relies on a temperature gradient. So we have a hot source and a cold reservoir. Notice that a lot of this stuff is from lecture that you're expected to know going in. So you just kind of breeze through that. But we are given thermal efficiency. And we're told that it's maximized with large differences between the cold and the hot reservoirs. Okay, and we're also given that on Earth the cold reservoir is limited to the ambient environment. Okay, so that's what you want to grab from the second paragraph. We get our equation. Okay, remember that you can't highlight in that because that's embedded. But do take a quick note of it as you move on. More italicized, we have a Rankine cycle. Okay, and we're told that that's a type of closed loop. And we were told about closed loops earlier, so that's something we want to highlight. And we're told it has 4 stages, and we're given those 4 stages. Okay, so 4 stages are easy to come back to if we're asked about them. Moving on over here, what do we have? We have thermal energy by rotating the turbine. We're told, so we're given the details about a steam turbine and how it works. Okay, so it's a type of Rankine engine, and we heat up the water, and the water is the thing that does the work to get it moving. Expanding steam does the work, okay, so that you might want to highlight. And then moving down just to get through it, the working fluid decreases temperature in cooling towers or system. Okay, so, and then we're told that water is often used as a cooling fluid. No big surprise there, but you could highlight that as something you may learn from text. Okay, so our passage is mapped, and now we go on to the questions. Okay, so the first one up. Which of the following is always the case for closed thermodynamic cycles? Okay, so first thing we want to answer is what's up with closed cycles, okay? Well, we're told earlier on that closed means there's no change. Okay, so that was back here. It's actually sentence 2. After one cycle, do not alter the internal energy of a closed system. Okay, so this means it's going to come back to where it started. So we know that change in energy equals 0. And since change of E equals Q minus W, and E is 0, then Q has to equal W. So that's going to get rid of Q equaling W gets rid of C and D. Okay, there's no difference between the two, so they have to be the same. Now, whether it's A or B is going to come down to how well we know our equation. Okay, in our original equation, change in E is equal to the heat minus the work done by system. Okay, so the work that we're calculating is the work done by the system, and that's how we get to A. Questions on that? Okay, moving on to number 2. Stage 2 of the Rankine cycle is an example of an. So we would go over here to stage 2. And stage 2 tells us that we have constant pressure.